This is your presenter Asloob Mudassar, and I am presenting slide number 70 of the course on laser physics. Question is, discuss the physics of absorption in a semiconductor material. Also discuss the relevant gain coefficient. The answer is, consider two energy levels E2 prime and E1 prime in the conduction and the valence bands respectively, with E2 prime minus E1 prime is equal to h nu naught. So we are considering two levels. E1 prime is the level within the valence band and E2 prime is a level within the conduction band, and we want to move the electron from the level E1 prime to the level E2 prime. And the difference of energies between these two levels is given by equation number 1, which is equal to h nu naught, where nu naught is the transition frequency. So as EC prime, that is the energy of a level in the conduction band, is equal to the EG plus EC, because we have set the level of measurement of energy at the vertex of the valence band. So above the valence band we have EG energy, and plus from the vertex of the conduction band to the upward we have the EC energy of the electron. So summing up these two energies will give you the energy of a level EC within the conduction band. So EC prime is equal to EG plus EC, and EV prime is equal to minus EV. And this is this EV prime is actually the value of the level EV within the valence band, because the energy will be measured negative, because we have set the reference of energy level at the top of the parabola of the valence band. So below that one the energy will be taken as negative. For that one you can see equation number 67.5 and 67.6. But in principle, in order to understand fully this lecture, you must you must consult the slide number 67. So using EC is equal to h bar square k square over 2 mc, where mc is the effective mass of the electron in the conduction band, and we can write EV as h bar square k square over 2 mv, where mv is the effective mass of the electron within the valence band. For that one you can consult equation number 67.1 and equation number 67.3. Now we can write E2 prime is equal to EG, because we are now want to write the energy state for the two levels as we have described above, that is E2 prime and E1 prime, because we are concerned with these two levels, and these two levels are actually the general levels within the conduction band and the valence band respectively. So we are writing E2 prime is equal to EG plus h bar square kc square over 2 mc. So here you see that we are using the wave number kc, and E1 prime can be written as minus h bar square kv square over 2 mv. Now we are applying for the transition to hold, we are applying the K selection rule. So for the transition to occur, K selection rule must be obeyed, and this K selection rule says that the wave number Kc for an electrons in the conduction band will be equal to the valence will equal to the wave number Kv for the electrons within the valence band. So Kc is equal to Kv in magnitude form. So we are setting these two wave numbers equal to the wave number K. And the last two equations then take the following form, that is E2 prime is equal to EG plus h bar square k square over 2 mc, and the second equation is E1 prime is equal to minus h bar square k square over 2 mv. So equation number 70.1 takes the following form. This equation is 70.1. Here we are writing for the next equation. To write from this equation, we are moving h nu naught on the right hand side and E2 prime minus E1 prime on the left hand side, along with the substitution of their respective values from equation number 2 and equation number 3. So the equation becomes h nu naught is equal to Eg plus h bar square k square over 2 mr. Here you notice that we have, since we have taken some terms common and we have rearranged the terms and introduced mr, where mr is the reduced mass of the electron, and mr is equal to mc into mp divided by mc plus mv. There are three unknowns, E2 prime, E1 prime and k. in the last three equations. The parameters of a single transition can thus be determined if these constants are known. So let's introduce rho j of E naught into d E naught as the density of transitions or density of states. You can say that we have previously introduced such quantities as density of states, and here we are using the word density of transitions as both statements are equivalent. So these rho of j of E naught multiplied by d E naught will give you the density of transitions with the transition energies lying between E naught and E naught plus d E naught. So in this energy range, that is from E naught to E naught plus d E naught, all the possible density of transitions will be given by this quantity, which is rho j of E naught multiplied by d E naught. Remember that E naught is our transition energy between the two levels, that is E1 prime level and E2 prime level. The exact value of the transition frequency between these two levels is E naught, and here we are writing rho j of E naught into d E naught, which gives the density of states for all the possible states lying in energy E naught to E naught plus d E naught. And here h nu naught is actually represents the E naught. So E naught is equal to h nu naught. Okay, so you see that we have applied over here the K selection rule for the transition. Now we are going to apply the spin selection rule. The spin selection rule, which says that delta S is equal to 0, that is the change in spin between the states in the conduction band and the states within the valence band will be 0. That is, both states will have the same spin, that is the levels in the conduction band and the levels in the valence band will have the same states. So this delta S is equal to 0 says that the two levels under the transition must have identical spins. This limits the number of transitions because we have applied some restrictions, so the number of transitions will be limited. And we have to find out those transitions which are limited so that we can find out the actual number of transitions. Let us use the relationship rho j of E naught into d E naught is equal to rho of k into dk, because both statements are equal. You know that energy is given by h nu, and nu can be represented as nu can be represented in terms of 1 over lambda, and you saw that when we have 1 over lambda we can introduce the wave number k. So both statements are becomes equal, either we represent it in terms of k or we represent in terms of energy. So we have rho j of E naught into d E naught is equal to rho of k into dk, where rho of k will give you the density of states or density of transitions lying between k naught and k naught plus delta plus dk. From here we can solve it for rho of j of E naught is equal to rho of k into dk over d E naught. This rho of k has been found through the calculations in previous slide, that is in slide number 69 or 67. So from the slide number 67 we can find that rho is equal to k square over pi square. Thus we can write rho j of E naught is equal to k square over pi square into dk over d E naught. So this is equation number 5. Solving equation number 70.4, that is this equation, for the value of k. So we want to solve this equation for the value of k and replacing h nu naught by E naught and obtaining dk over d E naught. So what we shall do is that we shall solve this equation for the value of k, that is k will be on the left hand side and all the quantities will be on the right hand side, and we shall replace h nu naught by E naught, and then from that equation we shall calculate dk over d E naught, that is the derivative of k with respect to E naught, and then plugging a k and its dk over de naught in equation number 5 over here, we shall obtain the following results. That is rho of j of e naught is equal to 1 over 2 pi square and 2 mr over h bar square raised to power 3 by 2 and then multiplied by e naught minus eg raised to power half, or the square root of e naught minus ej. We can also obtain the joint density of states. So this j actually represents the joint density of states. So we can obtain the joint density of states rho j of nu naught using the relationship rho j of nu naught multiplied by d nu naught is equal to rho j of e naught multiplied by d e naught, because both statements are equivalent. This is in terms of frequency nu naught, and this is in terms of this is in terms of energy e naught. But both represents the same thing. That is the both gives you the density of states. On the left hand side, we this gives you the density of states with the frequencies lying between nu naught and nu naught plus delta nu naught. Whereas the term on the right hand side, that is rho j of nu naught multiplied by d nu naught, will give you the density of transitions between the energy states lying between E naught and E naught plus delta plus d E naught. So solving it, we can write rho j of E naught is equal to rho j of E naught multiplied by d E naught over d nu naught, where j of E naught is obtained from equation number 70.6, and the derivative d E naught over d nu naught is obtained from this relationship, that is E naught is equal to h into nu naught. So if you take the derivative of this equation, d E naught over d nu naught, you will get that one equal to h. So substituting this over here in this relationship, that is we are replacing the derivative. So we are actually plugging the values in the equation. Rho j of nu naught is equal to rho j of E naught. This rho j of E naught will be obtained from equation number 70.6, and d E naught over d nu naught is obtained from E naught is equal to h nu naught, which is equal to h. So substituting these value over here, that is from equation number 70.6, and from the derivative of this equation, plugging these values, we get the equation shown in 7, that is rho j of nu naught is equal to 4 pi over h square multiplied by 2 mr raised to power 3 by 2, and then the square root of h nu naught minus eg. Now consider dn is equal to rho j of nu naught multiplied by d nu naught. We shall calling it as, what we call this as, this gives you the number of transitions with the frequency lying between nu naught and nu naught plus d nu naught. So here we are calling it the number of states or the number of transitions, or you can equivalently also say that the density of states. So lying between the nu naught and nu naught plus d nu naught, and we are representing this as the number of transitions represented by dn. So this is the elemental number of transitions represented by dn lying in the frequency range between the nu naught and nu naught plus delta nu naught. Out of these, the number of transitions available for absorption is given by, since this represents all the possible states, all the possible number of transitions, but you know that we are going to discuss the transitions which are available for absorption. So for that one, we are writing a term DNA. A stands for absorption. DNA, that is the elemental absorption, that is the elemental absorption transition, is equal to DNA is equal to dn, as we have stated above, multiplied by Fv of E1 star multiplied by 1 minus Fc of E2 star. So dn represents the total number of transitions. Now we are multiplying it with the two terms, Fv E1 prime and then 1 minus Fc of E2 prime. What these terms are, where Fv of E1 prime is the probability that the level E1 prime is full, and 1 minus Fc of E2 prime is the probability that the level E2 prime is empty, because we are using 1 minus Fc of E2 prime. So this stands for the probability that the level E2 prime is empty. So under that condition, you see that the lower level E1 prime has the we are considering its probability to be full, and we are considering the level E2 to be empty, so that we can consider the absorption from the level E1 prime to the level E2 prime. The ideal condition is that E1 prime, all the levels, because E1 prime, you know, that represents all the levels in the valence band, and E2 prime actually represents all the level in the conduction band, and we are considering them as specific levels over here. So we want that E1 should be fully filled and E2 prime should be empty, so that we can have absorption, maximum absorption from the valence band to the conduction band. To calculate the net absorption, we must subtract the number of stimulated emissions between the same two levels which are given by. So you see that when we try to do the stimulated absorption, there is also a possibility of stimulated emission also. So we have to subtract the possibility of number of stimulated emissions so that we can find out only the absorption numbers, that which we call as net absorption. So to calculate the net absorption, we must subtract the number of stimulated emissions between the same two levels which are given by. So we are now finding out the stimulated emission number, that is DNST. ST stands for stimulated, is equal to DN, which represents the total number of transitions, DN, multiplied by FC of E2 prime and multiplied by 1 minus FV of E1 prime. So you see that here FC of E2 prime represents the probability that the level E2 prime is fully occupied, and 1 minus FV of E1 prime represents the probability that the level E1 prime is empty. The elemental absorption coefficient. So you see that we are talking about absorption coefficient, but we are using the word elemental so that we can write not alpha but D alpha. The elemental absorption coefficient D alpha at frequency nu is obtained from D alpha is equal to D alpha is equal to sigma as a function of nu minus nu naught multiplied by dNA minus dNST, where dN is the total number of absorption, and from that one we are subtracting those which contribute stimulated emission. So this will give you only the elemental absorption coefficient, where sigma of nu minus nu naught is given by 2 pi square over 3n epsilon naught ch multiplied by nu multiplied by the absolute square of mu multiplied by g of nu minus nu naught. And you know that g of nu minus nu naught gives you the line broadening mechanism, and here we are considering the homogeneous line broadening. So this sigma of nu minus nu naught is the homogeneous cross section of the transition from E1 prime to the E2 prime. So equation number 10 thus takes the following form, because we are substituting the value of sigma into that equation, and we have d alpha is equal to 2 pi square over 3n epsilon naught ch multiplied by nu multiplied by the absolute square of mu multiplied by g of nu minus nu naught, and then the rest of the quantities over there which were dn, because we are now substituting the value of dna from equation number 9 over here, and dnst from equation number 9 and dna from equation number 8. So using equation number 8 and equation number 9 into equation number 10, and also introducing the value of sigma of nu minus nu naught, we obtain this equation, that is d alpha is equal to all these quantities, and the rest of the quantities is dn multiplied by, within the parentheses we have fv of E1 star minus fc of E2 star. F nu of E1 prime minus fc of E2 prime. So replacing dn by its value, we have this dn introduced, which represents all the possible transitions. And you know that dn which we have found is given by over here. So we have the expression of dn over here, which we have used over here. For example, this in red, dn is equal to rho of j of nu naught multiplied by d nu naught. So we are now substituting dn from here into this equation, and then we finally get this relationship, that is d alpha is equal to rest all the quantities are the same except that we have introduced rho j of nu naught and also d nu naught from the previous equation. So this becomes equation number 11. Now you see that this represents the elemental absorption coefficient, d alpha. Now we want to calculate alpha from this d alpha. So we have to do the integration process. But before that, in order to make a reasonable expressions, we assume that, let's assume that g of nu minus nu naught is much narrower compared with both rho j of nu naught and also with fv of e1 prime minus fc of e2 prime. So this function is narrower in comparison of both these functions shown in blue. Then g of nu minus nu naught can be approximated by delta of nu minus nu naught. Then under that condition, we can take the integral of both sides, and the left hand side integral is shown, which has integrand as rho j of nu naught multiplied by delta of nu minus nu naught and then d nu naught. So we have combined all the terms depending upon the nu naught within the integral. Now you see that using the property of the delta function, that this integral will survive when nu naught will be equal to nu. So under that condition, we have the expression given in equation number 12. And you see that we have only the dependence of this alpha function on the value of nu, where nu is the frequency of the incident beam. So this can also be written as alpha is equal to alpha naught, and we have the rest of the quantity in the bracket is fv of e1 prime minus fc of e2 prime, where alpha naught can be given as alpha naught is equal to 2 pi square over 3n epsilon naught ch multiplied by nu multiplied by absolute square of mu multiplied by rho j of nu, as given in equation number 14. For intrinsic semiconductor with Eg is much greater than kT, that is the energy band gap is much greater than the thermal energy for an intrinsic semiconductor, and this holds for the elements of group 3 to 5 semiconductors, where we have fv of e1 prime is equal to 1. That is the probability of the existence of the level 1 in the valence band is nearly 1, and the probability of the level 2 in the conduction band is nearly 0, that is the level is nearly empty. And you know that under that condition, when we set fv of e1 prime is equal to 1 and fc of e2 prime is equal to 0 and introduce these two values in equation number 30, we find that alpha is equal to alpha naught, which we have set over here in the head, that alpha is approximately equal to alpha naught, because these quantities are not exactly equal to 1 and not exactly equal to 0, but very close to them. That's why we have written alpha is approximately equal to alpha naught even at room temperature. So using rho j with nu naught replaced by nu, we have 4 pi of h bar. We have introduced rho j earlier, you know that. So we have 4 pi over h square multiplied by 2 mr raised to power 3 by 2, and then the square root of h nu minus eg. Here nu naught was present, which we have replaced by nu. And this is from equation number 70.7. So alpha in another form is given by, you see that we have found the value of alpha over here in equation number 12. Now we can also find alpha in another form, which is given over here, because we have introduced the value of rho j. Here we have the value of alpha on the value depending upon the value of j, rho j of nu. and here we have eliminated the value of rho j, and we have this full expression that the alpha is equal to alpha naught and equal to 8 pi cube over 3 and epsilon naught c into h cube, and then multiplying by nu, multiplying by absolute square of mu, and then 2 mr raised to power 3 by 2, and then the square root of h nu minus eg as given in equation number 15. Obviously alpha is characterized by the factor h nu minus eg whole raised to power half. If a semiconductor as a whole is in thermal equilibrium at temperature 0 Kelvin, the quasi-Fermi levels coincide with the Fermi levels. The quasi-Fermi levels coincide with the Fermi level, and if the level is within the energy gap, then Fv, because you see that at this temperature all the quasi-Fermi levels, you know that when we talk about quasi-Fermi levels, it means that the Fermi levels in the presence of some minorities added, some doping added to the semiconductor material. That's why we have the term quasi-Fermi levels. So the quasi-Fermi levels coincide with the Fermi level, and if the level is within the energy gap, then Fv of E1 prime will be equal to 1 and Fc of E2 prime will be equal to 0. Because you see that if these quasi-Fermi levels correspond to the Fermi level lying within the center of the energy gap, then you see that all the levels below that one lying in the valence band will be completely occupied, and all the levels in the conduction band above the Fermi levels will be empty. And then we can have alpha of nu is equal to alpha naught of nu naught. Okay, for the gain coefficient of an inverted semiconductor. So what is this inverted semiconductor? An inverted semiconductor refers to a semiconductor material where the type of majority carriers is inverted due to specific conditions. So notice that where the type of majority carriers is inverted due to specific conditions. This typically involves a p-n junction or a metal oxide semiconductor structure where the surface of a semiconductor layer exhibits opposite conductivity and opposite behavior. So you see that this is what inverted semiconductor means. And for that one we can write the gain is equal to minus times alpha is equal to alpha naught into Fc of E2 prime minus Fv of E1 prime. So you see that here we have introduced Fv of E1 prime minus Fc of E2 prime, and then we are multiplying with negative sign on both sides, so this will be inverted. So we have g of minus alpha, and we have also negative multiplied inside that one, but we have changed the order of these two terms within the parenthesis. So we have alpha naught of Fc of E2 prime minus Fv of E1 prime. The maximum gain is attained at 0 Kelvin. That is G max, that is the maximum gain, is equal to G at temperature 0 Kelvin, and that will be equal to alpha naught. The condition of the net gain is that Fc of E2 prime is greater than Fv of E1 prime. Now you see that the two levels are the two quasi-Fermi levels are now separated. And here you see that we were considering the condition when they were coinciding with the Fermi level of the band within the band gap. Now due to addition of the, and you see that now we are considering the inverted semiconductors where we have inverted the population of the majority carriers, and under that condition the two levels are separated, that is Fc of E2 prime and Fv of E1 prime are now separated, that is the two quasi-Fermi levels are separated. And then the probability that the level E2 prime in the conduction band is being occupied is greater than the level of the level E1 prime being occupied in the valence band. So it means that now the population has been inverted, because the E2 prime is now has a greater probability of being occupied than as compared with the level E1 in the valence band being occupied. So the conduction band has a majority of carriers in the conduction band. So you see that in terms of their full expressions, we are writing them as 1 over 1 plus e to the power E2 prime minus E prime of Fc and divided by Kt, and similarly the same relationship for the other quantity. And there is a greater sign between the two expressions. But you know that this is greater in the sense that E2 prime minus this quantity is actually a negative quantity, because E2 level is lying below the E prime Fc level, that is E2 level is lying below the quasi-Fermi level in the conduction band. So all E2 prime levels will be occupied. And you know that since E2 prime minus E prime Fc is a negative quantity as a whole, so at absolute zero we have a minus infinity over there. So e to the power minus infinity is 0, and 1 over 1 plus 0 is equal to 1. So the probability that the level E2 prime is being occupied under this condition is highest, which is closely equal to 1. And now let's analyze the other one. Here E1 prime minus EF prime. So E1 prime, you see that in the valence band now both are negative, but EF prime, that is the Fermi level, is more negative in comparison with the E1 prime. So this quantity becomes as a whole becomes a positive quantity, and at absolute zero what happens is that this becomes equal to plus infinity, and e to the plus infinity is equal to infinity. So 1 plus infinity in the denominator is equal to infinity. So we have 1 over infinity, which is equal to 0. So the level E1 prime being lying above the Fermi level in the valence band is empty level, whereas this E2 prime level is lying below the quasi-Fermi level in the conduction band. So this is completely filled. So this is what we have explained the inverted semiconductor over here through this expression, and we have also introduced the gain over there. So if we solve this inequality, we shall find that E2 prime minus E1 prime is less than the difference of their Fermi quasi-Fermi levels, that is EFC prime minus EFV prime, because you see that EFC prime is now lying in the conduction band is a positive quantity, and EFV prime is lying in the valence band being a negative quantity. But you know that E2 prime minus E1 prime is equal to h nu, because we want to do the absorption phenomena. So the light that will be incident having a frequency nu, and E2 prime minus E1 prime should have a energy difference that is equal to h nu of the energy of the incident beam, and that h nu is greater than Eg for a transition to occur. Thus we can combine all these inequalities as h nu is greater than Eg, and also h nu is less than the Fc, that is the EFC prime minus EFV prime, that is the difference between the quasi-Fermi levels, that is the in terms of energy. So h nu should be less than that one and should be greater than Eg, which establishes the gain bandwidth of the semiconductor. The limiting case is, you see that in the limiting case we have split the due to the doping, we have split the Fermi level into two levels. One level is Fc prime Now under this condition shown in equation number 17, this Fc prime is now lying at the vertex of the parabola representing a conduction band, and Fv prime, EFv prime is a quasi-Fermi level lying at the vertex of the parabola representing the valence band. So you see that the difference between two Fermi levels will be exactly equal to the Eg, which is the band gap energy between the two bands. That is, the Eg is the energy gap between the top of the valence band and the bottom of the conduction band. So under this condition is referred to as the transparency condition. In this case, the gain is equal to 0 at Eg is equal to h nu. Because if you supplying the energy of the incident beam equal to Eg, then you see that there will be no transitions, because the Fermi level, this Fermi level, which is this quasi-Fermi level, which is EFc prime, is lying at the bottom of the conduction band. So according to the definition, all the levels above the conduction band, above this level, will be empty. And you see that all the levels within the valence band lying below the EFv prime, that is lying below the quasi-Fermi level of the valence band, are completely filled. And you see that if you supply this much energy, then of course the transition will not occur, and the material is referred to as the transparent material, and this condition may be referred to as the transparency condition. To achieve this condition, one must inject a density of electrons into the conduction band, or equivalently a density of holes in the valence band, which is called the transparency density and is denoted by NTR. So to carry out the transition, we have to inject a density of electrons into the conduction band. If the density of the injected electrons Ne exceeds NTR, so you see that this transparency condition, so let me explain first of all that before the injection of any density carriers, the Fermi level was lying in the middle of the band gap. But if you have injected some density of electrons represented by NTR, because NTR corresponds to the transparency density. If you have injected transparency density, what will happen? The Fermi level will be split into two Fermi levels due to the injection of density of carriers. One will move, that is Fc prime, will move towards the vertex of the parabola, that is the vertex of the conduction band, and Fv prime, F and EFv prime will move towards the vertex of the valence band. So E prime Fc is lying at the vertex of the conduction band, and EF prime and E prime Fv is lying at the top, that is at the vertex of the valence band. So the difference is equal to Eg, and this difference is only created when you have incorporated an injection of in density of the carriers represented by NTR, that is the transparency density. Now if you inject, but if the density of injected electrons, if you inject Ne that is more than NTR, what will happen? F prime Fc minus E prime Fv. So E prime Fc minus E prime Fv, that is the difference between the two quasi-Fermi levels, will become greater than Eg. That is Fc prime, that is EFc prime, will now move to the conduction band, and E prime Fv will now move to the will move inside the valence band. So the difference between these two quasi-Fermi levels will be greater than Eg, and the net gain occurs for h nu is now greater than, has to be greater than Eg, that is the band gap, and has to be less than the difference of these two Fermi quasi-Fermi levels, that is EFC prime minus E prime FV. So this is the condition under which now the transition will occur. When Ne has exceeded NTR, which means that the quasi-Fermi level has moved to the conduction band and the other quasi-Fermi level has moved to the valence band. Increasing Ne increases quasi-Fermi energy difference, E prime Fc minus E prime Fv. So the more you have Ne, the more is the separation between the two Fermi levels, that is the difference will increase, and thus the gain bandwidth increases. Because h nu is less than the difference of these one. If the difference is greater, you have a more flexibility, that is more states will be available, or you can say that the gain bandwidth will increase with the increase of the difference between these two quasi-Fermi levels. That is, this will happen only when you increase Ne beyond the value of NTR. So typical gain coefficients of interest in semiconductor lasers lie in the range, that is the gain should be greater than 20 and should be less than equal to 80 centimeter inverse. So this parameter is required for most of the semiconductor lasers. So I think that the description is complete. So this is the end of slide number 70.